Hi, can you hear me?
Yes, sir.
Cool, thank you. So I'm again waiting for everyone to join. Uh, I guess it's a very busy day for everyone, so there's just three of us right now. I'm going to wait for another couple of minutes, otherwise we'll start. And the link to today's notebook is in the chat. We are not going to write any code today because we already implemented SARA and Q-learning. I just want to do a little walkthrough of my own solution and explain a few things, and then we will do a recap of what we did last week, and then I'll talk about the project rubric. So while others are joining, what you could do is just open the notebook and run through all the cells. Of course, this notebook was already present in the solutions folder, so maybe you have taken a look. uh, I have already, yeah. Most of it is going to look familiar because we implemented this on our own. Everyone you know, tried to implement their own version. We looked at the algorithm and tried to translate that to code. I just want to show you what my implementation looks like, and then talk about a couple of things that we can do to debug the training process if it's not converging, or if, you know, if we don't know how many episodes to run for. So just run the notebook. It won't take more than a few minutes. And right. So what we were trying to implement on Friday was basically the SARS algorithm, which we looked at the algorithm. It was pretty simple. The name itself was an abbreviation for state action reward state action, which meant that instead of taking an entire episode, let us just take two actions. So whatever our current state is, we will take one action using the epsilon greedy policy. and then we reach another state, and in the next state we again take some other action, again taking the same policy. That is the whole idea. And the reward that you get from this state transition, that along with the return from the next state, right, that gives us an estimate of the return of the first state. That was the whole idea. In terms of implementation, it doesn't look very different. We have just renamed our table. It used to be called estimated returns table. Now we're just calling it the Q table, which is the name you would see in literature. So it's still being initialized with all zeros. I'm going to come back to the hyperparameters, but in terms of the training loop, there isn't much of a difference. We're still starting. We are now starting with a state, and okay, there seems to be some issue. Give me a minute. There seems to be some issue with the Zoom link. Yeah. So we start with our initial state because we call reset, and then we pick an action using the greedy action policy, the epsilon greedy action policy, and then within this while loop we are sort of generating an entire episode. The only difference is that we are doing that one step at a time. So first of all, we execute the action A0 that we selected previously, that gives us the next state. Then while in the next state, we again select another action A1. This is what SARSA is about. So again select an action, and this action has to come based on the policy. The policy right now is epsilon greedy because we are in the learning process. So you pick A1, and then based on what A1 S1 are, we just execute our update step, which doesn't look very different from the episode based approach. The only difference is that now this first term, these two terms inside the bracket over here, these the sum is basically an estimate for the return of a state S0 and A0, right? Because the return is always made up of an immediate reward and then the return in the next state. So in this case, for SARSA, we are picking the return in the next state based on a random action or an epsilon greedy action, rather not a random action, epsilon greedy action, which will correspond to the best action most of the time, but occasionally it will be some other action. Right, that is the gist of the algorithm. Rest of the code is these two lines are basically epsilon decay, which we have already talked about. And if I let this algorithm run, then you can see that, and I'm printing the algorithm every 500, I'm printing the policy every 500 steps. So you can see that it starts to converge very quickly. Even maybe even by 500 steps, it has already converged. So this policy looks all right. We let it run for 2000 steps, and this, it seems that after converging, it has probably something has gone wrong. Probably we have overtrained. So what you get in the end is this policy, which doesn't quite look all right, but throughout most of the training process, the policies seem to be very quickly getting closer to what the optimal policy should look like, right? And I will come to how to sort of ascertain when to stop a little later. The other thing that we looked at was Q-learning, which is again, I'll actually like to go back and talk about the hyperparameters a little bit. So I just tuned it by trying different values. Of course, epsilon is equal to 1 is what we sort of decided we'll stick to, because we want to be uniformly random in the beginning. So I didn't change this parameter. The minimum epsilon value, I adjusted a little bit, but mostly epsilon decay and alpha were the parameters, hyperparameters that I tweaked. And after a little bit of experimentation, I was able to figure out that with 2000 steps and these values, I'm able to get convergence quite fast, right? And if you look back, if you look at the previous case over here, where we were using 5000 steps and we were using an episode based approach that was converging in 5000 steps. Now, of course, we will have to check if this can also converge in fewer steps. Uh, but then you also have to look at the overall training time, right? So maybe both of them are able to converge in 2000 steps, but 2000 steps, sorry, 2000 episodes, but 2000 episodes may take different time, because if one of the algorithm is learning much faster, then it will start performing efficient actions, taking efficient actions, or the best decisions very quickly early on during the first few hundred or thousand episodes, and so the episode length will drop. So you also have to look at the full episode length and then be able to compare. But even that aside, with this one, in general, feels like SARSA is being able to converge in just 500 episodes, which is one tenth of what we were using earlier, right? We can also implement Q-learning again using the same hyperparameters, but the only difference is now there is there is no A1 in state one. We just select the action that gives us the maximum return. This is the only difference, and this is why Q-learning is also called off policy, because whether you are using an on policy approach or off policy approach, the first action has to come from the policy that you are selecting. There is no other way, right? Because you have to simulate at least one step to interact with the environment and to gain some more experience. So that has to be there. But the second step in Q learning or off policy uh, approach, that doesn't require taking a real action, right? We just select whatever action will correspond to the maximum reward. That is what we implemented over here. There is not much of a change in the rest of the algorithm, of course, except for minor things like we don't have A1 over here, right? The rest of the strategy and the parameters, hyperparameters, everything is same. And this again seems to converge very quickly. Again, around 500 steps, this seems to have already converged. Uh, right. So this is just how I implemented it. There are other ways. There could be other ways to write the same code. You might want to abstract away the inner loop or stuff like that. Uh, but this is very simple. The core training logic is just made up of this for and while loop, which is hardly like 10 lines, maybe less. Right. Okay. So one thing we were discussing last time was, how do you find out when to stop? Is 2000 steps enough? Do we want to continue doing this? Of course, we can. We already have trained two algorithms. We have two different policies. We can actually put the policies to test. We can let them execute. Just start a game of foosball and feed it the policy, take actions according to the policy, and see how well it performs. But that is more a qualitative, uh, you know, assessment. If you want to do a quantitative one, then you need numbers. And one thing that we could do is fall back to the approach that we were using earlier when we were using dynamic programming. So the idea was that, okay, we are basically trying to update the Q table, and if the Q table stops updating by much, then there's no point in having more episodes. So what I have done is inserted a little bit of extra code over here. In the case of Q learning, uh, this won't be there in your copy of the notebook, but the idea is very simple, which is, first of all, before I enter the loop for every episode, I create a copy of the Q value, and then at the end of that episode, I take the difference of the before and after copies, and then I take the absolute values, and then I just sum over all the absolute values, right? So this gives me a single number. There are two tables, and this output just gives me a single number, which is sort of the difference between all the elements, uh, which is then added up. So this is the sum of differences, and then that is divided by the number of elements, which, sorry, this should be Q of 1, right? So this is just the product of dimension of the tables. So we make sure that we are measuring the average change in every entry in the table, right? And if you let this run, yeah. So I'm also recording that in an array which I'm calling Q deltas, and I have similar array for rewards as well, right? So what is happening is that there is this variable that I'm using to accumulate the reward for an entire episode. I initialize it to 0 right before an episode, and within at every step, whatever reward I get, I just accumulate it here, right? This is not discounted reward, this is normal reward, because when you're trying to measure the performance, you're not interested in discounting is uh, you know for the sake of training, because you don't want the agent to be too much reliant on rewards that are too far in the future. But when you want to measure performance, that you want to accumulate non-discounted returns. Non-discounted returns is what we are accumulating over here, and then when the episode ends, I just record it in this array, right? uh, so this algorithm seems to have trained. Now I can plot my delta, right? So these are all the deltas. This is by how much the table has changed. These are very small numbers, but and there is a lot of fluctuation going on as well, lots of spikes, but generally you can see that there seems like a downward trend. It's not very clear, but maybe perhaps if you think in terms of averaging, so perhaps the average over here was something like this. This was the average value, average change in the value of a straight action pair, the return value at this point. And then as the training proceeds, so that average becomes really smaller, right? uh, and there's a lot of noise. We can do something similar with rewards as well. This is the reward, the array where I have captured the reward for each of the 2000 steps, 2000 episodes. And again, there's a lot of variation. So because we have deliberately included randomness, so maybe there are times when something goes wrong because of randomness, or because there are times when the policy hits a state and action pair for which it hasn't really learned a good return value, so it takes a bad action, and that causes the reward to drop very steeply. Or sometimes you run into state action pair for which you have a very good estimate, so you get a very high return. uh, but this is over an entire episode. But there is still a lot of spikiness, very difficult to interpret, but you can see that there is what seems like an upward trend. So if the average was somewhere over here, it has increased to let's say this point, right? So if you look at an entire episode, and the you can say that the average return that you get is around 0, right? Uh, what we can do is, to get a better idea, we can take some sort of an average of these values or these values, and that is what I have done over here. So we take the rewards array. This is just going to be an array of size 2000, right? So this is an array of 2000. This is what I have plotted over here. But then what I want to do is I want to take a running average of this array. What that means is, I will start at episode 0. Let's say I'll take the average from episode 0 to episode 99, right? So that gives me 100, the average over 100 episodes. So if you average out, then probably there will be less noise and you'll see a clear trend. So that is what is sort of is going on over here. So there is a function called np.convol. If you are familiar with convolution, then it should make sense. If you aren't, then you can think of it as sliding a window over your data. So we have this data with 2000 entries, and we take a window of size 100, and the window is just filled with ones, and then you know, at every position the window is placed at, you take an element wise multiplication, and then you sum up things. So that is convolution. uh, and what convolution allows us is that once things are multiplied and added up, we can just divide them by 100 to get the mean. So if you want to implement a running mean, you can either write a for loop that goes to index I and picks all the elements from I to I plus 99, and then sums them up and then divides by 100, or you can use this np.convol function, right? And the division over here is basically because convolution just gives us the sum. It doesn't really divide by the number of entries, so we have to divide by that to get a real mean. If I run this, uh, this is the sort of graph that I get. Again, it's not labeled or anything, but we know that these are the rewards, these are the number of episodes. So there is still, like, there are still ups and downs. The algorithm learns, and then maybe there are times, occasions when it doesn't perform so well, then learn some more. But generally, this is going upward. So there are drops, but the value over here is still way better than the value that you had over here. Right? So rewards are increasing over time, even though there are spikes, right? And this seems to be happening till 2000 steps as well. So probably it makes sense to even go for more steps. Uh, we can do something similar for the delta values. Again, just convolving and finding the average. So again, delta drops very sharply, almost like parabolic or exponential shape, drops very sharply. Then again, there are some peaks in between, but it seems to be overall seems to be going down and down and down. So at no point there seems like a saturation. You will see graphs where after this phase there will come a phase where this line is just flat. So there are spikes, but generally the trend is very flattened out. That is not visible here, so it probably makes sense to train these algorithms for a little while longer, right? So this was the idea that we were discussing last time, and this is going to be an essential part of the debugging process when we look at more complex situations, uh, like our project. Cool. So this is all we wanted to discuss for the project. Let me know if there is any confusion, any questions about this. Then we'll move on to sort of the summary from last week, and then I'll talk briefly about some of the terminology that we have been avoiding deliberately for so long, and then of course our project.
Farhan, I had one question. So, based upon this rewards graph, how can I decide like what are my best hyper parameters, like number of episodes, or it might be epsilons or epsilon values, or even alpha. So, how can I decide by seeing this graph, Farhan?
Yeah. So you can't decide that by looking at just one graph.
Okay.
You will have to try out. So if you are just using trial and error, then you need to try out the different combinations. For example, change alpha, and then look at what the graph looks like, right? So plot this one and plot the next one and see if saturation comes earlier. Maybe with a larger value of alpha, 2000 episodes is too much because your graph just rises very quickly and then it saturates, right? Or maybe this has already saturated, but the value you're getting on the y-axis is very low, which means the algorithm is not able to learn anything new. Then you have to think about what to change. Should you increase the amount of randomness so the algorithm keeps changing? Should you change the learning rate? Should you reduce it? Should you make some other changes? So those things, but they can only be decided when you have several such plots for different hyperparameters. We are going to sort of discuss that when we start the project as well, because there of course you have hyperparameters. It is a more complex problem. It takes more time to train it and evaluate it, and you still want to find the best set of hyperparameters. So the most simplest approach would be to just write random values, like do a grid search over all the different combinations that you think will make sense, or you can do a random search over all the hyperparameters, and then for every time you conduct that search, whatever tuple you get or whatever combination you get, plot this. Of course you will have run the entire training process and evaluation process, but then plot this sort of a thing, and then see which one of your combination produces the best plot, the most desirable one. That will be the one where you reach your target reward in the least number of episodes.
And along with graphs, if I see this print prative policy which I'm printing for every 500 episodes,
Right.
uh, can I refer that also, like instead of
Yes.
plotting graphs, if I had seen for first 500 episodes, whatever policy it was printing, it was taking me into some it was taking me into the goal post actually. So
Correct.
if that is the case, can I depend on those rather than plotting the
Yeah.
graphs?
Yeah, in this case, I mean, you can of course refer to that, because the policy over here looks like it has learned everything. But
Yes, exactly.
you can definitely decide that, okay, we just need 500 steps. This, if you do this, if you plot the reward as well, that will just give you more information. In this case, it seems to suggest that the policy is still improving. Right now,
Okay.
this could be because it's a very small game. There are random actions going on, so probably there are too many random actions, and if you reduce the random actions, then you will get to this state, like you will get to convergence around 500 steps, but your reward will also sort of stabilize at that point.
Okay.
If you look at both, then you have more information to make that decision.
Okay. Sure. Thanks for.
Sure. Cool. So I'll try to summarize everything that we have learned so far. Uh, Again, we are over here in our course. If you look at this list over here, we have implemented most of this, but we may not have talked about them in terms of terminology, right? We are going to talk about the project in a little bit, but before that, I wanted to ensure that we also know the terminology, because if during the project you are referring to the website or any other resource, book or blog or anything, you should be able to understand that as well. So, uh, if you remember what we did essentially in week 3, so we sort of ended week 2 at the exploration dilemma, and we saw that we can combine both by having an array of values where you most of the actions had a small values, small probabilities, and the action that was the most optimum action, the one with the highest return, that could be assigned a larger probability. And when you sample from such an array using the probabilities, then you do a good mixing of exploration exploitation, and that seemed to work, right? Uh, this was the idea, and intuitively it makes sense to have exploration in the beginning and introduce exploitation a little later on, right? In terms of code, this pure exploration looked like just one line of code. This is what we had tried in week 2. uh, then we had tried pure exploitation, which was again a single line of code, just picking the index of the maximum action. This alone also didn't provide very good answers. When we combine both of these using this approach, which we were just talking about, then we for the first time we started getting okay results. We saw there was a trend, the policy seemed to improve, so that was very encouraging. Then we also saw that that we let us translate, or we thought about translating our intuition about slowly removing the randomness over time, and very simply we introduced epsilon decay, factor that let you reduce or take away most of the epsilon over time over different episodes. So this is what essentially we did at the beginning of the week 3, and then we asked, can we converge faster? Is there a way to learn faster? Because on such a very small dummy toy problem, you really want to squeeze the maximum performance, and you also want to use that performance to understand what other optimizations are possible. There could be optimizations in the code itself, but are there any theoretical improvements that people have already sort of found out about, right? The first thing we implemented was constant alpha, where we did away with the division by the number of visits to a state action pair. The idea was that division was causing every new return to have even a smaller uh, effect on the already accumulated values, because you were dividing by an even larger value every time, right? So the denominator kept growing and growing. So we just did away with that. We used a trick that we were using earlier as well. So we still had to update the table, the state action pair, the return value. So what we tried instead was, okay, let us take the return that we just got from an episode, and let's take the return that is already stored in the table. Let's take their difference. If there is a big difference, then I mean, there is something wrong. Either the table is not correct, or the latest return we have got from the episode is not correct. So whenever there's a difference, there's something wrong, and then based on that difference, we can make some course correction. So we'll update the table by a small amount by introducing alpha, right? And really, the next step was not doing an entire step at all, but sort of running the same process, the same. So we already implemented constant alpha. So I can how can we have this constant alpha kind of update, but every step of an episode? And that was the whole idea behind SARSA and Q-learning, which are collectively known as temporal difference (TD learning), because you are using the difference between two steps, the reward that you get by taking two steps between two states to update the table, right? And of course, when you introduce this, then we have to go back, because we no more have access to an entire episode at a point. So we have to go back and think about using the recursive equations that we were using earlier in case of dynamic approach. So that is what we did. We saw that the state and action, if you look at any state and action and you want to compute its return, that return could be thought of as being composed of two different things: the immediate reward and the return in the next state, right? The difference is that in case of dynamic programming, because we had the sort of inside information, we always took the maximum value from the four possibilities. So in the next state, we always took the maximum, the 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 value corresponding, the maximum value corresponding to the best action, right? In this case, we don't know because this table is still evolving, so we don't want to sort of pick that value every time. So we decided that we will pick an action using the same policy that with which we selected the action on the left side, right? But other than this trick, again, this was an incremental change over the previous approach. We just saw today that this is giving us good results. This is the algorithm again, very short, 5-10 lines. And then Q learning, basically we already discussed that. Instead of what we did just discussed, that you need to pick one of the actions epsilon greedily in the next state, you can just again use an approach which is similar to the dynamic programming approach, where you just select maximum all the time, right? And then I shared a few links last week about what the difference is. So hopefully the difference is clear to everyone. But then when do you want to select Q learning versus SARSA, and why they are called online versus on policy versus off policy? So I shared three different links on those topics. As far as performance is compared, Q learning is used more often, because if you look at the literature, if you look at the links I shared, they say that Q learning is able to directly converge to the optimum policy, and SARSA has to be, sort of, you have to be very careful with it to let it converge to the optimum policy, right? We are not going to look at the theory behind that or the derivation or any proof or any guarantees, but we should bear this in mind, and we will see going forward that generally people implement Q-learning and get slightly better results with Q-learning. Um, so now I want to spend some time going over the terminology that we have seen in bits and pieces, right? So we started with the environment and agent. The idea was that whenever you have planning and control problem, can we divide it? Can we model it as an agent that is working inside the environment or interacting with the environment? So the agent is sort of carrying out actions, and the environment and the agent, they have some sort of a state. The state changes over time, and then you all, for every action you also get some sort of a reward or penalty from the environment, right? And we have seen this diagram. One thing to remember is that the distinction or the boundary line between environment and agent is not as clear as we might think, and we saw that with the simple example of foosball, right? So if you talk about the state of the environment, if you think of the player as the agent, right, and the rest of everything else like the opponents and the goalposts and everything else being the environment, then the environment doesn't really have any pieces that change position, or the values get updated. But if you think about the state, the information that we want to track, the information that we want to feed to our algorithm, that state includes the position of the ball. It has to have access to that information to make intelligent decisions. So in that sense, the state of uh, the agent is included in the larger state which you want to feed, right? So you can think of the state being part of the environment state, or you know you can think of the state as being made up of the state of the agent and the state of the environment. But that distinction, you will have to think about that distinction for every new problem, right? In fact, if you refer to the book, so Sutton and Bardo book, which is linked as a reference in the Slack channel, you will see that they talk about exactly this thing, that the boundary can be located at different places, and it will depend on what you define as your state. Uh, then, of course, state, we wanted to define state in terms of all the information or a description of the environment and the agent. That is what we defined the state as. Uh, and the decisions that the agent was taking were the actions. Now, there is a very subtle difference that we haven't really talked about, that, but you will see when you're referring to books and other sources, that there is something called a state, and then there's something called an observation. And the idea is that the state can be really complex. So if you think of a robot that is looking at it has a camera and it's looking at a scene, so the state is basically all the pixel data, or the video footage or the stream that the robot is consuming. But observation will be only the part of the state that the algorithm is actually using, right? So there may be many ways in which state and observation differ. One could be that some of the state is hidden, so the agent is not able to look at it at all. The other possibility is that there is a state, but the state is in a very raw form, like this one, the robot example, right? So if the state is very raw, you want to first convert it into observations, something that the agent, that the algorithm can interpret. So in that case, probably there will be some computer vision algorithm that lets you segment or identify objects or whatever, and that will be the observation that you want to feed to your algorithm. Right now, our state has been so simple; it's been just an integer, so this distinction is not very clear. But in the case of taxi environment, and then when we evolve our foosball environment to include more moving pieces, then you will see that state and observations have to be discriminated, like they are two different things, right? And then you will see MDP being referred to Markov decision process. Of course, decision process refers to what sort of problems that we are solving, where you have a state, action, state kind of a chain. But these sort of have a property which upon which all the solutions are based. We haven't really talked about that, and that property is that you only need to know about the current state. You just don't need to, like, if you want to make decisions, if you want to determine the future of the environment, then you just need to be looking at the current state of the environment. You don't need to be looking at the previous or past state of the environment, right? That is an assumption we haven't really talked a lot about, but if you refer to the books, then this assumption is used in many places. Right. But generally, the problems we are solving, they fall into the category of MDP. If something is not an MDP, then probably you will need to convert into an MDP so that your current state has all the history. So you never have to refer back to previous states, and then you can apply the same techniques. Uh, there is a little bit of notation as well, right? So states can of course be represented as sets if we talk about them mathematically. Actions can also be sets, and then MDPs have transitions because of course they're made up of different states and actions. So like I said, they're sort of a chain or graphs. So you can think of the different transitions that are possible as a function. So as a function or a table that you can call P, which is so it's it takes a state and action pair. So this is like the cross is the Cartesian product. So it takes all possible, its domain is all possible state and action pairs, and then its range is all the states, right? So it will, if you think of it as a function in terms of programming, then it takes a state and an action pair, and then it produces a new state. If you think of it as in terms of mathematics, then its domain is these tuples, and then its range is again the same space, the space of the states, right? So if you think of the set of all the states, you can call that the state space, and the set of all the actions, that is your action space. And this function maps from a Cartesian product of the state and action space into uh, the state space. And you can similarly think of the reward matrix or the reward function as well, which is again a function that takes a pair of states, the current state and the next state, and that maps it to some real number R. So this represents a real number. This R is our reward matrix or reward function. There is one more thing which we haven't really seen right now, which is that right now we have been looking at deterministic environments where you take an action and you are 100% certain about what your next state is going to be, right? And in those cases, this is what the transition matrix of function looks like. So there's a state, an action, and there is an output state. When this is not the case, when there is non-determinism, when the environment is stochastic, you take an action and there are multiple states possible, right? So in that case, this will make more sense when we look at one such case. But in that case, the function or the table is uh, it takes a state, action, and a possible next state, and maps that to a probability, right? So for example, if the foosball were non-deterministic, if we were in state 0 and we took action east, then there could be multiple possibilities. One of those possibilities will be that this next state is state 1, and probably its probability will be zero point 0.8, zero point 0.9, something like that. But there could be other possibilities as well. Probably the agent will slip and reach state right below it, which will be state 4. So this is over here will be 4, and then that will have some small probability associated with it, 0.1, 0.01, whatever. And similarly for other states, right? And so this is sort of the more generalized form where you have to consider that the environment is going to be stochastic. So actions are not perfect anymore. Single step dynamics, we have already referred to it, but we really didn't use the term. But single step dynamics is basically your transition table and your reward tables or reward functions, right? These are generally things that are hidden from us, and that is the whole reason why we want to learn them, or we sort of want to learn decision making while we are not able to directly look at the single step dynamics. So we don't know what states are possible, we don't know what transitions are possible, what the rewards are, what those probabilities are. We still want to learn the best course of action, the policy. Right, reward return, discounted return, we have spoken about it at length, so I'm going to skip over this. There is some notation over here which we sort of already saw in the previous session. So R was the reward and G was the return. And of course, we have seen what discounting is. Policy, very simply, we already know that intuitively policy is the guideline that you have to follow. So the agent has to follow, which means that policy tells you which action to take in a state, right? Now that policy could be deterministic, like this one, that just says that it will take a state as an action and put state as an input and produces action as an output. It could also be like an epsilon greedy policy, which is stochastic. So that will take two inputs. It will take a state and action pair, and it will produce a probability. It will tell you, okay, with this probability you can take this action. With this probability you can take this action. So again, this will assume two different forms depending on whether your policy is deterministic or not. One thing to bear in mind is that the policies we are looking at right now, their final form, that is when you are sure that the algorithm is trained, we always use the greedy policy, which is deterministic in nature. So when we think that okay, the Q table has converged, we want to derive the final policy, that is always a deterministic policy. So even if the environment may not be deterministic, we have somehow managed to find out a deterministic policy. So whenever we are in a particular state, we know which action to take. Even though there is a small chance that we will miss that action and the outcome will be something else, we know this information and we will always use this deterministic policy, right?
One question
Uh,
here.
yeah,
So when we implement the policies, right? So basically, if we have a stochastic condition where we might end up in a terminal state, so maybe we will avoid that kind of scenario also, right? When we implement that, and means avoid in the sense we start giving less weightage or something. So suppose if we have equal probabilities between two, we have to choose, and then yeah. So I think you got my question.
yeah. So the issue there is that policies are based on return values, right? And these return values are based on experience, and these are just when the environment is stochastic, then these are just estimated values, right? So maybe you followed the same action in the same state twice, but once you were successful, like not twice, maybe 10 times. So 8 times you were successful, 2 times you failed, you ran into a terminal state, right? So the policy will still rank that action as being good as opposed to other actions, because
So yeah,
the
so
expectation,
basically yeah, so that means basically in it is built into that action,
right?
basically in the even the stochastic thing. Okay.
Yeah. And much later, I think in course 3 we'll start to talk about policies where you can have a truly stochastic policy that gives you a distribution, that gives you a choice to pick the action.
Okay.
So generally, when you look at the literature, so the pi is the policy, and then the optimal policy that you eventually want to learn, that is denoted by pi stars, so small asterisk at the top. Uh, yeah, one thing we have been using for a long time, but we haven't really given a name to it, was the Q table. So we've been calling it the returns table, but this is actually called the action value function, for the simple reason that this tells you for every state, for every action, what is the best return that I can get, right? So that is generally known as the action value and denoted by Q. And of course, the action value will always correspond to a policy from which it has been learned. So there is always this pi at the bottom. There is also a concept of state value, which is in every state there will be four different action values. In this case, because there are four different actions, in a general case there could be n different actions, so there could be n different action values, uh, q values. But state value is basically the best return you can get irrespective of the actions. So you just take a maximum or all the actions and argmax, and whatever action gives you the best return, your state value correspond to that return, right? So we haven't explicitly used state values, but if you go back to the code over here, right, especially the code for Q-learning. So if you look at this part, right, this you can just, if notationally you want to describe it, this could be your v value. This is your state value because this is the maximum across all actions. It doesn't care about the action, it just gives you the best return. So and sometimes when you're looking at algorithms, just like uh, a multi-step approach where you start with a policy, right, you follow the policy, and then from there you compute the state value and the action value, and then you use that to create a new policy, and then that this thing goes on. So if you're reading through the book or this very long blog that I have referred to, so you will see that there is, we go to, right, so it refers to something called GPI, which is policy iteration. It's a very simple idea that you start with the policy, then you find the state value, then you improve the policy using the update equations that we saw, then you again find a new policy. So this repetitive process, and this will involve not just v but q values as well. So when you are improving, you require q values and v values both, so state and action values. But this is the general idea of reinforcement learning. Yeah, the other thing we haven't given a name to is our estimation technique, where we are sampling things. So that is known as Monte Carlo estimation. Again, this is not just restricted to reinforcement learning. It's a general technique where you are trying to learn something, the value of a function perhaps by sampling it many times. There, if you look up the internet for this term, you will see many interesting applications. Like if you want to find the area of a very irregular sort of shape, right? So how do you do that if you don't have a formula for measuring the area? So you can take random samples, and then based on how you can take random points, maybe, so first of all, maybe draw a circle or a rectangle or a square that just sits, so that the shape is within that rectangle or regular shape. So this irregular shape is entirely within the regular shape, and then you pick random points, lots of random points within that larger area, right? Sometimes those points will be inside both, like the intersection of the area. Sometimes they'll be just inside the outer area, and you should take the ratio of the count of points which are inside the intersection versus those that are within the union. So that gives you an estimate of the area, because you're picking points at random. So there is no such bias or anything, so the point is equally like to be anywhere. So depending on how many points are within the larger the area inside your irregular curve, the more probability there is. And that is why when you take the ratio, you're taking the ratio of probabilities, and that gives you an estimate of the area of that irregular curve. So the idea being that this is being used elsewhere as well, not specific to reinforcement learning. But in our case, the idea is very simple. We don't know about the single step dynamics, so we are going to sample, and the only way to sample the environment is by interacting with it. So that is the technique that we've been using. And There are a couple of links if you want to learn more about it. One more thing which we not really only terminology, but we haven't really touched upon this. But when we were doing episode-based learning, then there is generally a distinction in if you look at books and elsewhere, then you will see that what we were doing is every time you visited a state and action pair, we would update its return value basically, right? When we were using the Monte Carlo's and approach based on generating an entire episode. Uh, there is a dissection. There are two different sub cases. The one we were using was every visit, of course. The other approach is first visit, where so of course you can think of the different scenarios. If a state and action happens to occur more than once inside an episode, then which of the two return values should you use? Should you use the first one or the second one or both of them? So there are some subtle differences between the two approaches. Some implementations will use first visit, so you will only consider, you'll keep track of whether or not this is the first visit within an episode, and if only if it is the first visit, then you update its return values. If you want to know about what those differences are, then again refer to the book, Barto and Sutton. Uh, so, but yeah, this we should be aware of this. Uh, Greedy policy we have already seen. Greedy with respect to return, it just means that pick the action that has the highest return there. This we have gone with this. Epsilon greedy, of course, is a combination of both approaches. We have seen Q and V as being the action value function and the state value function. Again, if there's a star over them, then they represent the optimal state or the optimal action value. This is what you eventually want to learn. And likewise, pi star is the optimal policy, right? The what I was just showing you a while back about policy iteration is made up of two steps. So first one is evaluation, where you know some policy. That policy could be quite bad because you're just getting started or whatever it is, but you have some policy in place, and then using that policy you generate v values, right? State values you estimate, q values, right? That is sort of the first part, first step. And then the second step is policy improvement. So when you generate those steps, sorry, when you generate those values, then you can use them to get a new policy, because policy is just, you know, created from a q table or a v table. So this is sort of the two steps that I showed you here. So evaluation and improvement, that make up what is called as policy iteration. Then very important part which we have sort of sidelined so far, which is the so-called Bellman equations. I'm still not going to talk about them today because there is some leftover work at the end of week 4 when we are familiar with the stochastic environments. Then I'm going to come back and show you the Bellman equations. For now, this slide is empty. Explosion exploitation and epsilon decay we have already covered. So that is everything, almost everything we need to know about all the terminology that is used when you are referring to reinforcement learning. Of course, there will be more terminology when we learn about deep reinforcement learning, and a lot more when we start looking at specific algorithms. But right now, this should prepare you for checking out any blogs, any resource, and you won't feel like this is something new that you don't know. Right? So feel free to the slides; they are over here in week 3 office hours. So these are the slides. Again, the best way to view them will be to just sync this repository and view them offline. And what I want to do now is very quickly give you an overview of the project. I know we are just on time, uh, but in the same folder in W3OH, you have the starter code for the project. It's not much of a starter code, just a few lines just to show you how to create the environment, because the idea is to let you figure out what to do next. But there are two important things. This is a starter code. You may use it, you may not use it. If you want to work offline, that is also fine. Or if you want to use Python scripts, not notebooks, that is also fine. But you also have the rubric files with the 5 different rubric criteria that we have to meet. Right. So before the project is submitted, you have to ensure that you meet all these criteria. Very quickly going back to this one, right? So Gym is now we are going to use the OpenAI Gym environment. That is something I mentioned in the beginning, that we are building our own environment, and one of the reasons was that we want to understand how these environments are built that way with those APIs. So now it's time to start looking at Gym itself. There is we I have linked the environment over here. You can read more about OpenAI and Gym here, but basically it's already imported and installed in Google Colab, right? So you can directly go ahead and import it. Then the way you create an environment is by calling this gym.make method, which is like factory method. So instead of directly calling the the initializer or the constructor for the class, this is the right way to do it. So you do this, and then you should be looking at this point. You will have taxi. You can just start looking at what different fields are there, what different methods are there. But if you want to look at the number of actions, then you need to look at this variable called action space, which is a class that basically describes how many the type of the actions and the size of the action space. And observation space, like I said, this is your number of states, right? So in this case, for taxi environment, both are discrete because you're just dealing with discrete environments. There are 6 different actions and 500 different states. Now again, how there are 5 different states, that is already explained in the documentation, and that is something that we also sort of need to figure out during the project, like when you're doing the project, right? The next thing we need to do is just call the reset and render methods. Right. Again, this rendering will only make sense when you look at the documentation. There's some color coding going on, but very quickly, the yellow thing, the yellow rectangle you see over here is the taxi, because the whole idea of this project, this environment, is to learn to navigate this taxi. So this is the taxi, and then there are 4 different locations where from where you can pick up or drop off passengers, and you basically have to learn when to pick up, where to go, and then how to drop off, right? uh, so right now, like, you know what the project is, you know what the rubric is, so you can get started right now. But even before attempting to solve the environment, uh, I would want everyone to take a very close look at the environment, explore the environment the way we did with our own foosball environment, because you will only get to you will have you will only have sufficient information when you do that right now. You can read through the documentation, but until you do that, you experimentally interact with the environment, you won't feel confident. So do that, manually interact with the environment, write a script to interact with the environment. There are a few things we have gone over this project with one of the earlier cohorts, and that there were at least a couple of very interesting findings that people found out about, which didn't seem to be documented anywhere at all. But when they looked at the problem very closely, when they tried to solve it, iteratively, and they tried to debug situations, then they found out about these really interesting pieces. So the whole idea is that, you know get started on the project. We have this entire week, we also have the next week, right? So after our last like after this week, you get an additional week to work on the project. uh, I'm here to clarify the rubric items and everything, but probably it is a bit too early right now to be looking at the rubric items. The first step would be to just explore the environment. If you look at the rubric, then obviously the first 2 points right here, they actually ask you to describe what the discrete environment class is, what the taxi v3 class is, how they are structured, what the different methods are doing, what fields are present. So anyway, you have to do that deep dive. And then of course you have to use the same algorithms that we have learned about. The algorithms, you don't necessarily need to change the algorithms. If you want to change them, that is also fine. But what we really need to figure out are the right hyperparameters that get us the right performance. And the most important part is going to understand how to debug a problem like this, right? So even figuring out the right hyperparameters, how do you go about it? How do you find the right one? Even if you are doing just trial and error, uh, can there be additional stuff that you can do, like we were discussing a while back? How can you compare two different pairs of, or two different combinations of hyperparameters? That is sort of the most important part. And then of course, once the algorithm is working, then you need to look at the performance criteria, which is point 4 and 5. Right, so 4 and 5 basically is the performance that you have to reach. Yep. That's all in today's session. We will meet on Thursday. Right. We will have our first session of the last week on Thursday. I think Friday is a day off in Qualcomm, if I'm not wrong. So we will have to conduct the Friday session next week sometime. Uh, we can decide whether we want to do that next Thursday, of like in the week after that, which would be, I think, 20th. Or if we want to do it sooner, probably wrap up on Monday. If everyone has time, then we can also do that on Monday itself. We will have to take out some additional time. So, but yeah, any questions about the project, anything, let me know on Slack, or if you want to ask right now, that is also fine.
Thank you for having.
Cool. Thank you. The project is officially open. I'm going to make an announcement in the channel as well. So whenever you feel like it, whenever you have time, take out some time and attempt to solve it. If there are any issues, let me know. Uh,
Hi Farhan.
because yeah,
Yeah, so I have given a try with the gym as well, and
right,
I see that sometimes there is no issue with pickup and drop. Like we will get even if we train around like 3,000 to 4,000 episodes, the pick and drop will be the, it's like they are always be zero. It's like there is no illegal pick and drop.
right.
The issue comes is like the path it follows. It will not take the shortest route. So is there any metric? It's like I was trying to find out like uh, is there any metric to find the shortest path? Because everything we are doing is averaging out, and we are not giving like this must take the shortest path.
Yeah. So the first thing probably we need to do is write that sort of pretty print sort of function for this case
Okay.
that just lets you look at the policy. It's not going to be as straightforward because now the state is something different. It's not just a rectangular
Yeah, yeah.
matrix.
Because the state became too much complicated, so
Yeah, the
it's
state is
even
complex. Think about how you can probably decompose the problem so that you have fewer states and you can sort of overlay it on top of a rectangular grid and you can just see, okay, what is the policy telling me for every state. One thing people have tried is just breaking up the policy into two pieces. So one is the policy that tells you how to perform the pickup, and then the part of the policy that tells you how you can do a drop off. So if you can segregate the two parts, if then you can probably plot what the pickup looks like, right? uh, and with that, the other thing of course you want to plot is how the reward is changing, the accumulated reward, no discounting. So probably you just need to, because you said 3 to 5 thousand steps, so maybe the 3 to 5 thousand steps are not adequate, right? So even though
it's like around 7,000 steps. It is like going the shortest path. But I was trying to find out the correct traffic parameter.
right,
Yeah, we'll
So
give a try like to set the
so people have also tried like because in this case we have access to the internals. You can even benchmark your learn policy against the shortest path algorithm, right? Just write
yeah.
BFS algorithm, you know where the
Yeah, I
people.
thought of that one, but yeah, I didn't get time to write the bill.
Right. So it will take some time to figure that out. But yeah, basic things like does the algorithm still have an appetite to learn further? Are there any issues? Is there too much randomness? Is there too little randomness? So stuff like that. Once you have figured that out, then you will have a better understanding of which things to try next. Maybe simply just trying for 10,000 steps will solve the problem. Cool. Ping me in Slack if there is any issue at any time. Thank you.